Well, here we are again. It's the physics video lecture, psci 168, video lecture 10. Today's topic is motion. So we had done all manner of discussion of energy, vectors, and so forth. We have to do a thorough study of motion this time. Next time I'll teach you how to calculate the speed of an orbiting satellite. So we'll get a bonus there, learn about satellite orbiting, satellites orbiting the Earth. But for now we have to get into the basic concepts of motion. Things moving. And I'm going to motivate it with the, I was going to say the hammer and the feather. I'll actually just hold the hammer up here, but I've got a tennis ball as well. So the type of motion we're going to talk about is, first of all, falling motion. So let's see, I've got this apparatus here. Maybe I'll take this down for the moment. Okay. Yeah, so we're talking about motion. We're going to talk about falling motion. And the first thing we have to do is compare the falling motion of a hammer and a feather. And I'm not going to drop the hammer on the desk, but the hammer falls like a hammer, like you'd expect, and the feather, here, I'll drop the hammer on the book. Okay, the feather drops like you'd expect. There we go, stay put. Good. Once more with feeling. Okay, this is what you'd expect. Okay, the feather takes a while to fall. The hammer just falls like a piece of metal. And when I do this, I often demonstrate a number of other objects falling. I can take paper, I can crumple it up, you could actually drop a leaf. You're going to find many different types of falling motion. But, so let's actually make a little list while we're at it. So the first thing we're talking about is falling motion. Things falling, and I have a hammer, a feather, and you can add to the list, and maybe you guys want to actually try dropping a couple of things side by side. Paper, etc. Leaves. Okay, they seem to fall differently. However, there's an interesting thing here. So I'm going to drop a book and a feather. This is the law of falling motion. Okay, the book just seems to fall pretty much like the hammer. Feather just floats down. Okay. Now, here's a demonstration we can do. If I just put the feather on top of the book, and you're going to notice it's not sticking. Feather on top of the book and drop it. It fell directly with the book. This feather fell just like a hammer, like a rock, like a brick. Okay. And so what's the explanation of that? So by the way, this is a good demonstration you guys can amaze your friends with. Okay, you just put the feather on the book. It's not sticking. Oops. You drop it, it falls with the book like a rock. The explanation is that the friction from the air resistance has been eliminated. Okay, the book went ahead of the air. So this is our next topic, and it's called free fall. So this feather, exclamation point, free fall is fall in which friction has been eliminated or sufficiently eliminated. I'll just say fall without friction. You can say air resistance, wind resistance. We've experienced these kinds of things. Fall without friction. And the law of free fall is that all objects fall the same if there's no air resistance, no friction. So literally the feather, if you took it to the moon where there's no atmosphere, it would drop side by side with the hammer, okay? So that's a really important point. So the law of free fall, I'll even write this out. The law of free fall is that in the absence of friction, all objects fall the same. So, absent friction, all objects fall the same. Okay, so this is, it says absent. All objects fall the same. So that hammers, feathers, tennis balls, people, cats and dogs, okay, a brick, a chunk of metal, they're all going to fall exactly the same. And now the question is, what is the nature of that law? So if this is the general statement, can we make it more precise? In particular, we want to make it mathematically precise. Okay? And we're going to find the mathematical law of free fall in a moment in the course of this hour. So that's our goal. And these are things you have access to. You have any number of objects, you can drop them. By the way, this demonstration that I did with a feather also works well with a flat sheet of paper. Let me see if I can find one. Of course I can. So yeah, we can do the comparison. You know, the paper and the feather, very similar. And right, the paper here held flat falls very slow. Okay, you put it on top of the book, even though the book it overlaps a bit. Actually, I should have tried this first. Okay, it's not sticking. Put it on top of the book. It falls. Boom, falls with the book. Okay, so there's proof. That's a demonstration you guys can do if you want to try it on your own. So where are we? All objects fall the same. So next, the nature of free fall. And what we're talking about is the mathematical nature. We're going to make that more precise. Okay, so I'm going to bring that track back. So what we have to do, 1, 2, 3, 4. We have to set up a set of concepts of motion. And for that purpose, I'll bring in our track again. Here we go. Hammer can go over here. Okay, so this next board is going to be concepts, kinematic concepts. So now we're calling this motion, kinematic concepts. And there's just a list that we have to go through and understand. Okay. So the first thing is we have position, and think of the position on a number line. 0, 1, 2, 3, 4, 5. I could say it's position X, and say I'm measuring meters. Okay. So here's a meter stick, and I'm representing 1, 2, 3, 4, 5 meters on my number line here. And we can certainly also go -1, -2. Or the position could be vertical. Okay. Also X in meters, 0, 1, 2, etc. Or it could be on a slope. Okay, so we're talking about the position, and I got another color here. Here's A, and I could say X of A is equal to, what is it equal to? 1.5 meters looks like. 1.5 meters. So there's position. What's that thing? The next concept, so we're using the metric system, by the way. We're using the metric system. The next concept here, by the way, position x, is called displacement. And the displacement is going to be called delta x, and it's x final minus x initial, or I could say x b minus x of a, and that's what happens, or it represents moving something, the change of position, right? Change of position, put that down here, change of position. And this displacement is also going to be measured in meters, because if I move to the right, let's do this. This is B. So I put the B at 3 meters, and I had the x of A, the A at the 1.5 meters. So my example, delta x equals xb minus xa equals 3 meters minus 1.5 meters, 1.5 meters. So I moved something, say 1.5 meters. And if I started at B and went to A, then it would be minus, right? So this was a positive direction. The reverse of it would be a negative direction. So we can have positive and negative numbers. So good. This list of concepts, position, displacement. The third one, I'll stick it here, it'll fit, is velocity. And velocity we're going to call V, and that's going to be delta x divided by t. We can also say a delta t. This is meters and this is seconds. So this is displacement per time so velocity, we put the square bracket around to tell us what the units are. Meters per second, I'll write it out. Speed and velocity are not the same thing, but we may use them interchangeably under certain circumstances. Okay, because there's nothing uncommon about this. A distance over a time, or a displacement over a time, we use the expression driving so and so many miles per hour, right? That's the speed, and the miles represents the displacement, and the hours represent the time. So here it's meters per second. I'm going to give a very simple example. V equals 100 meters divided by 10 seconds. So why did I choose 100 meters divided by 10 seconds? Well, the 100 meter dash is run in roughly 10 seconds by the world-class athletes. In fact, a little bit less than 10 seconds. Now we'll go with 10 seconds. What we're going to get out of this is 10 meters per second. So now you know 10 meters per second is the speed that a human being can run. Okay, 10 meters per second. So that's an example. So we have so far position, displacement, velocity. The list goes on, but it only goes on once more. So I'm going to erase these. And you can make up more examples of these, of course. In fact, while we're at it, before we make up those other examples, here I've got a car, and it moves, once more, it moves very smoothly. And the question is, how fast was it going right now? Well, here's a meter stick. And I'll just send this here, 1001, 1002. Took 2 seconds to go 1 meter. So how fast was it moving? So one more example, which I'll squeeze in right here. V was equal to 1 meter, 2 seconds. So that's 1/2 or 0.5 meters per second. So anything's possible, okay, in terms of these velocities. Good. So position, displacement, velocity, these shouldn't be causing you any trouble. Now we're going to get the last concept here. And I'll leave the velocity here at the bottom. This is the interesting one. So if you're looking at this progression here, you might think, well, what if we take the change of velocity? And that's what we're going to do. So for acceleration, and acceleration we'll call the letter A. It's the change in velocity over the time. You know what? I'm going to go ahead and put a delta t here. You can correct your notes. Talking about delta t or t, it's essentially the same thing. Okay. When we plug in numbers, we may say that time is so and so many seconds, the way I did, but the formulas are more symmetric this way. So where are we? The acceleration is the change in the velocity over the change in time. So if you're speeding up and slowing down, you are accelerating. So speeding up or slowing down are examples of acceleration. Speeding up or slowing down. There's a vector nature to all these quantities that I don't want to get into, because you could actually have the same speed and be changing direction. But for our purposes, we're just going to say acceleration, speeding up or slowing down, the change in velocity over the time. And we're going to find the units of acceleration. So square bracket means, put this as a note, square bracket tells us the unit of that quantity. And what we have here is in the numerator, meters per second, just like here. And in the denominator, seconds. Okay, so when you multiply that out, or divide it, as it were, you're going to get meters per second squared. So the units of acceleration, meters per second squared. Let's go ahead and write that out as well. Meters per second squared, and when we say that, we mean exactly this: a meter divided by seconds to the second power, second squared. So what's an example of accelerated motion? Examples. When you're at the traffic stop, light is red and it turns green, you push on the accelerator pedal in your car and you accelerate forward. What happens? Your speed changes from 0 to some final speed, and it takes a certain amount of time to happen. Okay. So examples, I'll just write here: in traffic, and there are many examples of that type. But let's look at something else that picks up speed. If I drop this tennis ball, it starts out at rest, and by the time it hits my hand, it's moving. Okay, it changed speed, right? Changed velocity. And it took a certain amount of time to do it. Okay, like 1001, took a certain amount of time to fall. So free fall, which is what we're studying, is a form of accelerated motion. So free fall. Free fall is accelerated motion. now we have some concepts, 1, 2, 3, 4, displacement, position, displacement, velocity, acceleration. And we're going to be able to get a little more out of that. Traffic, I'll write here in traffic, etc. You have as many examples as you want, but free fall in particular. And let me say something else about free fall. If I throw the ball in the air and catch it, as soon as it leaves my hand, it's in free fall. As it's going up, because it's slowing down and coming to a stop, it's accelerating. And it stops momentarily and picks up speed in the down direction. It's still accelerating. So the acceleration in free fall is both on the way up and on the way down. And again, why? Because the velocity is changing that whole time. So now I have a demonstration, and you guys can do this as a home project as well, to investigate free fall a little more. So let's go ahead and title this Galileo and free fall. And by the way, now's the time to look up Galileo somewhere online. You do a little reading on Galileo and maybe get his picture, and put something about Galileo in your book. Okay. Image. This will be great. Galileo's a true hero of science. So Galileo is the one who figured out the nature of free fall, and his idea was to slow down the motion because it happens too fast if you're just throwing a ball up in the air. He said, okay, I'll roll a ball down an incline, and I can make the incline steeper and steeper, and if I make it vertical, it's true free fall. But here it's going to be the same as free fall, but slowed down. And he had this idea. He didn't have a good clock yet. Good clock had not yet been invented. So in order to get good time data without a clock, he used his sense of rhythm. And I'm going to draw what he did. Okay. He rolled things down the inclined plane. Oops. He rolls a ball down the inclined plane, puts a little groove in it, and makes some little tiny object that'll make a clicking sound when the ball rolls by. And of course, it's picking up speed on the downslope, so he has to increase the separation distance. Let's even add one more down here. So the last distance would have been here, and 0, 1, 2, 3, 4 even spaced clicks. Okay. So he's rolling the ball down the groove. There's a little metal leaf or something, a little metal spring, something that's going to make a slight clicking sound when it goes by. Click, 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 in even rhythm, and that's his clock. Okay. So here, this is the inclined plane. And these 0, 1, 2, 3, 4, this is 0, 1, 2, 3, 4 are clicks, evenly spaced clicks. Okay. And this is some little ball that's rolling. Okay, so how can we do that? A little difficult to build an inclined plane and all of this, but there's a very nice little project we can do that's going to do the same thing, except we're going to do it vertically. So I want to leave this picture up here, and I'll write the rest of it here. So am I numbering things still? Yeah, 6. So what we're going to call this is the drop chord. So 6, 7, the drop chord. Okay. And I brought the ingredients here to class. Let's see if we can pull this off. I'll get rid of this track once again. Okay, this is our drop cord project. You see I have feathers and crumpled up paper and what have you. But what's most important, I have a string and a ruler. I'm going to unwrap this string here. Let's see if I have all my ingredients. Yeah. Okay, I'm going to take this pen here and I anchor it in I anchor the string in this pen, so I just got the loop of string here. Now along my ruler, I'm going to stretch out this string here, and I have clips. These kind of clips I'll clip them to the string. Let's see. Use the big ones or the little ones. Let's see, we'll use the little ones. Okay, so I have different size clips. Got these from the office. I'm going to put these clips at a well-defined distance that I know. Galileo had to do this by trial and error. I know the answer, which I'm going to share with you, but there are the precise separation distances that will allow us to get the even time. And the even time is something we don't need a clock for. We have our sense of rhythm. Okay. Wish me luck. I don't even know if this is all going to fit in the camera frame, but we'll do it anyway. Okay. So I have 1, 2, 3, 4 clips. I'll remove this ruler here. And I'm going to use this as a soundboard. Stand on a chair and then I'll make this work. Let's draw a picture of what we have here for the drop cord. We have, you can use a pot or a pan or something for the soundboard. This is a good home project for you guys, by the way. Okay. So I just have a string here. I've anchored this to my pen because I wanted to rest here. You'll see, and now I've put clips at apparently increasing separations. So these are clips. And when I drop this thing, it's supposed, it's going to hit 1, 2, 3, 4. And the idea is an even time. Okay. Just like Galileo rolled them down the slope, 1, 2, 3, 4, even times. It's picking up speed on the way down, so we know it's accelerated motion. Okay, let's see now. Can we pull this off? This stuff here. Hammers and feathers. I'll go grab a chair. Not sure if we're going to come out of the frame or not, but let's give this a try. Here we go. Wish me luck. This may be out of the frame, but try to hear it. Okay, I'll do a couple of repeats of this. Uh-oh. Ready? Right. Right here. Looks like I have ready. Once more. I heard the last 3 were very even, so listen carefully. Missed. Okay, this is your project, your home project. Once more. Okay, that was a success. Okay, nobody was hurt. No injuries. Okay, that's the drop cord. I'll lay this out again, and I'm going to give you the data for it now. You're not going to be, you'll be able to do this standing on the floor. It'll work just fine. Okay, I'll give you the data. the even beats I think we heard, especially on the last one. So what we have here is the following. 8, drop chord data. I will make a chart here, time, distance fallen, okay. So we had 0, 1, 2, 3, 4. Those were the times. The instant I released it was 0, and then 1, 2, 3, 4, evenly spaced times. So the units don't matter. We don't know if it's a second or a half second or what, but it's evenly spaced. The distance fallen was 0, 10 centimeters, 40 centimeters, 90 centimeters, and 160 centimeters. Okay. Another way to look at this is that I took 10 centimeters as my unit of length. Okay, that's the unit of length right here between the pen and the flip. That's a 10 centimeter length. And so if that's 1 unit of length, then 40 is 4, 90 is 9, 160 is 16 of those units. And the law that we see here is that the distance fallen goes as the time squared, okay? Because 0, 1, 2, 3, 4, 0, 1, 4, 9, 16. So we find distance fallen is proportional to the square of the time. Proportional to time squared. Okay, or write that down in words if you want. Distance fallen is proportional to the time squared. Now there's a proportionality constant here, but we don't know what it is. It depends on the units that we choose. Okay. If we use inches, it'll be different than if we use centimeters. But it will always be distance fallen proportional to time squared, because we just took a unit, which just happened to be 10 centimeters. Now, we've gotten a lot farther now with our law of free fall, and I'm going to draw one conclusion here, or d over t squared is constant. That's what it means to have a proportionality. D divided by t squared, I'm just dividing both sides by t squared, is constant. So let me pick up here at the left side of the board. And here, this was 9. If my list is still accurate, 10. This d over t squared, if we ask what are the units of d over t squared? What are the units? Well, we just learned about those units. The units are meters over second squared. Those are the units of acceleration. What we just discovered is that the law of free fall is that the acceleration is constant. So let's even underline this constant over here. Yeah, the first and last time that we get such a great law of nature on the spot through our in-class demonstration. So the units are acceleration, and 11, free fall is falling motion with constant acceleration. Okay, free fall is motion with constant acceleration. And that is going to take us far. Exclamation points. So what we can say for what you'd like to do is make one of these. Okay, it's easy with clips. It would probably even work with paper clips. These are some kind of paper clip after all. And just some piece of string. You'll see how I have my string stored on something because otherwise everything gets tangled. So clips are the best. It's better clips than trying to tie a knot on something, okay? So homework would be to make your own drop cord and see if it works, and you can report on it in your notes that you turn in. So construct a drop cord. And you'll see, you have a little more time and a better space to do it in. You can get a very impressive result if you have a good soundboard and you don't miss it and it's not muffled, so you get a clear ding, 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 right? 4. I said 4, but what if we had a 5th one? What if we had a 5th one? I'm going to put question mark here. You could put this in your notes as well, and you could build one. You stand on a ladder, you get the next height, okay? Or you could choose a smaller increment. If you started with 5 centimeters, you'd have a more compact drop cord, etc. So go ahead and construct a drop cord. Get a picture of it in your notes, and realize we're discovering the law of free fall. Let me consult the time now. See how much time we've got left. Oh, this is probably getting on to a good spot to finish. I'm going to do one more thing. Okay. So free fall is motion with constant acceleration. So for point 11, I'm going to write down the free fall equations, okay? These we could also test out. We have found the most important thing by doing our demonstration. These equations are just algebraic consequences. And I'll think about if I may or may not derive them next time, but right now, let's just call these the free fall equations. The kinematic free fall equations. So, object is going to be released from rest. Just like when I drop a hammer, a feather, a tennis ball, I'm releasing it from rest. Then distance fallen, I'll just call it D. Well, we're going to be using H a lot. Maybe I'll call it H. Distance fallen, H, is equal to 1/2 GT squared. So this constant that I'm talking about here, constant acceleration, this constant is this 1/2 times G. G is called the gravitational acceleration, 9.8 meters per second squared. But you see it's got that T squared law. That was our drop cord proved to us. This 9.8, and 9.8 divided by 2 is 4.9, we could get with simple experiments. In fact, you guys may want to even play around with that. If you drop something, for example, T equals 1 second, then what is H equal to? If T equals 1 second, 1 squared is 1. 9.8 over 2 is 4.9. So H would be 4.9 meters. Well, this is a meter stick, 4.9 of those. Let's see, here's 1, 2. Top of this board is 2, so what you can see in the image here is probably 2.5 meters. So 4.9 is up there. That's how far something falls in 1 second. Let's do one more little example. If t equals 1/2 of a second, 0.5 seconds, h will be 1/2 g t squared. The half g is 4.9. The 1/2 squared is 1/4 meters. But what's 4.9 over 4? That's just under 1.2. No. Yeah, just under 1.2 meters. 1.25 meters, approximately, let's write approximately 1.25 meters. So that's one you could test. If you drop something, here's 1.25 meters, okay. That's 1 second. Okay. So that is something you can test out with a stopwatch. In fact, if you have your camera, your phone camera on slow motion, then you should be able to drop something 1.25 meters and time it out to be 1/2 of a second. So you might want to even try that. Let me put that down as well. That's a homework suggestion. Here, I'll put this in a red squiggly box. That's a homework suggestion. If you can pull it off, not bad. Test that out. Slow motion on your camera. You do a lot of stuff. Okay, for now we'll leave it at this. What we're going to do next time, possibly a bit more with these, but we're going to do satellite orbits. And in fact, the satellite orbit, although you can't tell right now, it's going to follow. It's going to actually follow from what we've already learned. So I'll put here next 12, next horizontal throw and satellite orbits. And here, it's a little box right here. Satellite orbits. Good. Enjoy. See you guys next time.